Hello, this is a revision video for AP Chemistry, Chapter 4, Chemical Reactions. As this is a revision video, only the essential information is covered. For more detailed explanations and full video lessons, please check the links in the description below. Good luck revising.
Matter can undergo changes that are classified as either physical or chemical. Understanding the difference between the two is fundamental to recognizing what kind of transformation has taken place. In a physical change, the composition of the substance stays the same, but its form or appearance changes. No new substances are created. Common examples include phase changes, such as melting, freezing, evaporation, condensation, and sublimation, mixing substances without a chemical reaction, for example sugar dissolving in water, and changes in physical size or shape, such as cutting or grinding. In all of these cases, the chemical identity of the substance is unchanged. For example, when water changes state from solid to liquid to gas, it is still made up of molecules of H2O, meaning the chemical composition hasn't changed, only the arrangement of the molecules in the substance, meaning the changing of state is a physical process rather than a chemical process. A chemical change, also called a chemical reaction, results in the formation of one or more new substances with different chemical compositions and properties. Indicators of a chemical change occurring may include color change, formation of a gas such as bubbling or fizzing, precipitate formation, so a solid forming in a liquid solution, heat or light given off, and a change in odour, smell, due to the formation of a new substance. For example, if a carboxylic acid is added to a solid sample of sodium hydrogen carbonate, carbon dioxide gas is released, and this is observed as bubbling or effervescence in the liquid, and the solid slowly disappears. This indicates a chemical change has taken place, and it's a change in chemical composition. Exam tip here: always look for observable evidence when trying to determine if a change is physical or chemical. But remember, not every color change or temperature change automatically signifies a chemical reaction. You sometimes need to link different bits of evidence together to determine and recognize chemical change. In a chemical reaction, atoms are rearranged into new substances. A balanced equation reflects this by showing the correct chemical formulas of all reactants and products and equal numbers of each atom on both sides of the equation. For example, when hydrogen reacts with chlorine to produce hydrogen chloride, we can represent this with a balanced chemical equation as H2 plus Cl2 goes to form 2HCl. Each side has 2 hydrogen atoms and 2 chlorine atoms, meaning the total mass of reactants on the left is the same as the total mass of products. And as both reactants are neutral and have no overall charge, then the product's neutral and has no overall charge, there's no change in charge. Exam tip here: actually remember that balanced equations show molar ratios. So for the example given previously with hydrogen and chlorine, what this equation actually shows us is that 1 mole's worth of hydrogen reacts with 1 mole's worth of chlorine to produce 2 mole's worth of HCl. In aqueous reactions, we can often write 3 different forms of the equation taking place. We have a molecular equation, which shows all substances as if they were molecules and weren't broken apart in the liquid. The complete ionic equation, which shows all ions dissociated from soluble ionic compounds, and the net ionic equation, which removes ions that don't actually change in the reaction. These are called spectator ions. For example, hydrochloric acid can react with sodium hydroxide solution to form sodium chloride and water. The full molecular equation for this would be HCl plus NaOH goes to form NaCl plus H2O. The complete ionic equation would be H plus Cl plus Na plus OH goes to form Na plus Cl plus H2O. Here we have shown how the substances actually exist in solution, dissociated into ions. The net ionic equation, however, would simply be H plus OH going to form H2O, because if you look carefully at the complete ionic equation, Cl- and Na plus ions remain unchanged. They're both on the left and right side of the equation, meaning they are spectator ions and don't take part in the chemical reaction. leaving us with H plus OH goes to form H2O. Exam tip here: if you're ever asked to write a net ionic equation, always start by writing the full molecular equation. Then break all strong electrolytes or ionic compounds into ions and identify and cancel out the spectator ions. Check that the total number of atoms of each element are balanced along with charges, and you'll always get to the right net ionic equation. Don't skip steps. When writing balanced equations in chemistry, we always follow two conservation laws: conservation in mass and conservation of charge. Conservation of mass means the total number of atoms of each element is constant and doesn't change, and the conservation of charge means the total charge of all species before the reaction is the same as after the reaction. These two laws are universal and always apply, so make sure when you're writing equations both of these laws are followed. Particulate representations, also called particulate level diagrams or molecular level models, illustrate chemical and physical changes by showing individual particles interacting and rearranging. These visual models are especially helpful for understanding how reactants become products in a reaction and the role of spectator ions. They can also quickly indicate stoichiometric ratios in a balanced equation and changes in physical state. For example, the precipitation reaction between silver nitrate and sodium chloride to make silver chloride and sodium nitrate can be represented using a particulate representation. We would show the silver and nitrate ions along with the sodium and chloride ions as being independent of one another, dissolved in solution at the start. However, because the formed silver chloride is a precipitate, we would show the silver and chloride ions being tightly clumped together, creating particles of solid in the product. The nitrate and sodium ions would still be independent of one another in the solution, indicating they are spectator ions and haven't taken part in the reaction. This is a visual representation then of the net ionic equation Ag plus Cl minus to AgCl. Physical changes can also be represented using particulate level diagrams. Particles in a solid are shown tightly packed together, unable to move, with minimal space between particles. In a liquid, particles are still shown as being close together and touching one another, but there is gaps between them and they can move freely. They aren't held in fixed positions. A good particulate representation always uses shapes or symbols to represent each kind of atom or ion. For example, larger ions can be represented with larger circles and smaller ions with smaller circles. They show the correct number of particles on each side to reflect the balanced reaction equation. And states of matter are clearly indicated when relevant. So for particulate level diagrams involving gases, particles are shown spread out, independent of one another, solids are shown in fixed tight arrangements, and aqueous ions are shown freely moving independently amongst solvent particles. Chemical processes involve the breaking of intramolecular bonds and the formation of new intramolecular bonds to create different substances. By intramolecular bonds, we mean bonds between atoms or ions, for example covalent or ionic. During the formation of new substances, often observable macroscopic changes take place, for example heat energy being released, color changes, precipitation, and gas formation. For example, in the combustion of methane, CH4, carbon-hydrogen bonds in the starting methane have to be broken, and oxygen double bonds in the oxygen molecules also have to be broken, before new double bonds between carbon and oxygen and new single bonds between oxygen and hydrogen can be formed to make the products carbon dioxide and water. Physical changes involve no breaking of intramolecular chemical bonds, only changes in intermolecular forces, for example hydrogen bonding and London dispersion forces. These changes don't produce new substances, just different forms or arrangements of particles of the same substance. For example, when water melts from a solid to a liquid, hydrogen bonds between water molecules get broken and the molecules rearrange themselves. And if liquid water is then boiled or evaporated to produce individual gaseous molecules of H2O, all the hydrogen bonds between water molecules have been overcome. However, the molecules themselves remain the same, so solid ice, liquid water, and gaseous water are all made up of the same H2O molecules. Only intermolecular forces have been broken when the state of water has changed. Some cases are borderline and blur the line between chemical and physical change, such as the dissolution of ionic salts in water. When an ionic compound dissolves in water, Ionic bonding in the crystal lattice gets broken, whilst at the same time there's a formation of ion-dipole interactions between ions in the compound and surrounding water molecules. However, no substance is actually formed, so it can be argued as being both a physical and a chemical process, depending on the context. Exam tip here: when deciding if a process is chemical or physical, ask yourself, are the chemical bonds between atoms changing? If yes, then it's probably a chemical process. If no, and only phase or structural changes are occurring, then it's a physical process. Always have a look for observable changes or any extra data given in a question to help make your decision, because it isn't always clear-cut and straightforward. A balanced chemical equation shows the smallest whole number ratio of reacting species. The coefficients shown in a balanced equation refer to molar ratios. So for example, 2H2 plus O2 to form 2H2O actually tells us that the molar ratio is 2 moles of H2 to 1 mole of O2, forming 2 moles of H2O. This stoichiometric balance and molar ratio given by a balanced equation is incredibly useful and important when dealing with calculations and amounts of substance in chemistry. There are several key equations you need to know for dealing with amounts of substance. N equals m over mr, with n being number of moles, m being mass in grams, mr being molar mass, so mass in grams of 1 mole of the substance, n equals m times v, again n being moles, m being molarity, and v being volume. So molarity is the number of moles in 1 litre of solution, and volume is the volume of the solution in litres. And N equals PV over RT. This is for ideal gases, with N again being moles, P being pressure, V being volume, R being the universal gas constant, and T being temperature. And the number of particles, N, in a substance can be calculated by taking the moles of the substance times by Avogadro's constant. It is really important you can use and rearrange these equations as required. Exam tip here: when calculating or converting molar amounts, always make sure you check your units thoroughly and carefully. For example, volume with solution calculations must be in litres for molarity, and temperature for the ideal gas equation must be in Kelvin. The limiting reagent in a given reaction is the reactant that will determine how much product can be formed. In other words, there isn't enough of this reactant to react with all of the other reactants, which are in excess. A yield refers to how much of a product gets formed in a reaction. A theoretical yield is calculated from the moles of limiting reagent. It is the maximum theoretical amount of product can be formed based upon the amount of starting reactants, or limiting reagent. Remember, it is theoretical, and this amount is never actually obtained. The actual yield is the amount of product that you do obtain or isolate in a reaction. The percentage yield of a reaction compares the theoretical yield to the actual yield, so how much of your product you actually obtained compared to how much you could have obtained theoretically. It is calculated by taking the actual yield, dividing it by the theoretical yield, and timesing it by 100. Remember, at the same temperature and pressure, the volume ratios of gases are the same as molar ratios, so you can use them interchangeably. So for example, 2H2 gas plus O2 gas goes to form 2H2O liquid. Well, the 2 moles of H2 plus O2 could equally be expressed in volume, so 2 litres of H2 gas would react with 1 litre of oxygen gas, because the number of moles of gas in 1 litre of either gas will be the same. But remember, this is from an ideal gas assumption. A titration is an analytical technique used to determine the concentration of an unknown solution, the analyte, by reacting it with a solution of known concentration, the titrant. Titrations are particularly useful when a reaction occurs completely and predictably between the two substances, for example, an acid-base reaction. The equivalence point in a titration occurs when the amount of titrant added exactly reacts with all of the analyte present at the start. The moles of titrant and analyte have been mixed in the correct stoichiometric ratio shown with the balanced reaction equation. For example, a simple 1-to-1 ratio for an acid-base reaction is HA plus O minus goes to form A minus plus H2O. The equivalence point is reached here when the moles of OH minus added equals the moles of HA in the starting solution. The end point in a titration occurs when enough titrant has been added to cause an observable color change by an indicator in the solution changing color. This is used to signify that the equivalence point has been reached in the titration. For example, the indicator phenolphthalein turns pink in alkaline solution. So in a titration between a strong acid and strong base, the end point is reached when the indicator permanently changes colour to a faint pink colour. Notice here that the endpoint and equivalence point in a titration aren't actually the same thing, but we want them to occur at the same point. So an indicator should be chosen that will have an endpoint that should match the equivalence point for the given reaction. So for an acid-base titration, the pH that will cause an indicator to change colour should be the same pH achieved when the acid and base react together perfectly. Exam tip here: when using titration-based data, always write the balanced chemical equation first to identify the correct molar ratio between titrant and analyte. Keep all units consistent, especially volumes used, and be precise when reading from your burette. You should always read the burette from eye level and always make sure the bottom of the meniscus is on the line being measured, the meniscus being the curved shape of water in a narrow container. Reactions in chemistry often follow similar patterns and can be classified into groups. There are several groups that you should be aware of for this course. Acid-base reactions involve a transfer of protons, H+ ions, from one species to another, with the acid acting as a proton donor and the base a proton acceptor. This is based on the Brønsted-Lowry definition of acids and bases. For example, HCl plus NaOH goes to form NaCl plus H2O. Here, this is an acid-base reaction because a H+ ion is transferred from the HCl to the OH- from the sodium hydroxide. Water is formed from H+ plus OH- going to form H2O. The HCl is acting as an acid and the NaOH a base. Redox reactions involve the transfer of electrons and include oxidation and reduction. Oxidation refers to the loss of electrons by a species and an increase in its oxidation number. Reduction refers to the gain of electrons by a species and a decrease in its oxidation number. Exam tip here: remember that in a redox reaction, electrons are transferred from the species that is oxidized to the species that is reduced. For example, when zinc reacts with copper ions to form zinc ions and copper, the zinc gets oxidized from an oxidation number of 0 to positive 2, an increase in oxidation number. It has lost 2 electrons. And the copper 2+ ion gets reduced from an oxidation number of positive 2 to 0, so the copper has gained the 2 electrons lost by the zinc. A combustion reaction is a type of redox reaction where a substance reacts with oxygen. For example, when carbon combusts and reacts with oxygen, it gets oxidized. Its oxidation state changes from 0 to positive 4. Precipitation reactions occur when two aqueous ionic solutions react together to form an insoluble solid or precipitate. For example, silver nitrate plus sodium chloride goes to form silver chloride and sodium nitrate. The silver chloride that gets formed is insoluble and forms a white precipitate. So two aqueous ionic solutions, AgNO3 and NaCl, have reacted together and formed an insoluble solid, AgCl, meaning this would be a precipitation reaction, and the AgCl is the solid precipitate. Oxidation numbers can be really useful to help us track electron transfer in reactions and identify redox reactions, determining which species gets oxidized and which gets reduced. There are some basic rules to follow for oxidation numbers, although some exceptions do exist. Elements in their standard state are always assigned an oxidation number of 0. Group 1 metals in compounds have oxidation numbers of positive 1, Group 2 metals in compounds have oxidation states of positive 2, and hydrogen always has an oxidation state of positive 1 unless it is bonded with a metal, in which case it has a negative 1 oxidation number. Oxygen always has an oxidation state of negative 2 in a compound unless it's in a peroxide. For example, hydrogen peroxide, H2O2, it has an oxidation number of -1. The sum of oxidation numbers in a compound equals the charge of the species. An acid-base reaction is one in which a proton, H+ ion, is transferred from one substance to another. The substance that donates the H+ ion is called the acid, and the substance that accepts the H+ ion is called the base. This is the Brønsted-Lowry definition of acids and bases, where a Brønsted-Lowry acid is a H+ ion donor and a Brønsted-Lowry base is a H+ ion acceptor. In aqueous solutions, H+ ions are never found alone. They bond with water molecules to form hydronium ions, H3O+. The H3O+ ion is carrying the H+ ion from the acid, and it's the H3O+ ion that actually then goes on to react with any added base. As a result, H+ aqueous and H3O+ aqueous are interchangeable in chemical equations. They represent the same thing. But using H3O+ gives a slightly more accurate picture of what happens in solution. For example, if HCl is added to water, it dissociates and forms H3O+ ions and Cl- ions. Now, the HCl is donating a H+ ion here, so it's acting as the acid, and according to the Brønsted-Lowry definition, because the H2O is accepting a H+ ion, it is acting as a base. We say the H3O+ is the conjugate acid of H2O and Cl- is the conjugate base of HCl. An acid-base pair consists of two species that differ by a single proton. Every acid has what's called a conjugate base, and every base has what's called its conjugate acid. This sounds a lot more complicated than it is. What we mean is when an acid loses a H+ ion, it forms its conjugate base. And when a base accepts a H+ ion, it forms its conjugate acid. For example, when ammonia reacts with water, it forms NH4+ and OH-. The NH3 accepts a H+ ion from the water and so forms its conjugate acid, NH4+. So the conjugate acid of NH3 is NH4+, an ammonium ion. Equally, the H2O has acted as an acid because it's donated a H+ ion and therefore forms its conjugate base, OH-. So the conjugate base of H2O is OH-, a hydroxide ion. Acids and bases can be different strengths. The strength of an acid or base refers to how easily it can donate or accept H+ ions. Strong acids donate H+ ions easily, and strong bases accept H+ ions easily. As a result, the conjugate base of a strong acid is a very weak base. It doesn't easily accept H+ ions to reform the strong acid. For example, the strong acid HCl easily donates H+ ions and forms its conjugate base, Cl-. But this Cl- ion is a very weak base. It doesn't easily accept H+ ions to reform the strong acid HCl. Equally, strong bases have weak conjugate acids. So for example, the strong base OH- has a weak conjugate acid of H2O. The H2O doesn't easily donate H+ ions, meaning it's a very weak acid. The relative strengths of acids and bases are covered in a lot more detail under Chapter 8, Acids and Bases. A redox reaction involves the transfer of electrons between two species. The species that loses electrons undergoes oxidation, and the species that gains electrons undergoes reduction. You can remember this as oil-rig. Oxidation is loss of electrons, and reduction is gain of electrons. So for example, with the reaction between zinc and copper ions, zinc loses 2 electrons and gets oxidized, and the copper ions gain 2 electrons and get reduced. To help track electron transfer a little bit more, redox reactions can be split into 2 parts, called half reactions or half equations. The oxidation half reaction shows the species losing electrons, and the reduction half reaction shows the species gaining electrons. Each half reaction must be balanced for the atoms and charges involved. So for the zinc and copper example just shown, the oxidation of the zinc would be shown as zinc going to form zinc 2+ plus 2E-, and the reduction of the copper ions would be Cu2+ plus 2E- goes to form Cu. So we are showing the oxidation and reduction steps in the redox reaction independently. Half equations can be combined together to give the net ionic equation that's occurring. Exam tip here: when combining 2 half reactions together, the number of electrons lost by the oxidized species must be the same as the number of electrons gained by the reduced species. For example, If zinc was reacting with chlorine, the half equations would be zinc goes to form zinc 2 plus 2e minus, and half Cl2 plus E minus goes to form Cl minus. Now, to combine these two half equations together, we'd have to multiply the chlorine reduction by 2, so the same number of electrons being lost by the zinc are being gained by chlorine. So this would now be Cl2 plus 2e minus goes to form 2Cl minus. We can now combine the two half reactions together to give us Zn plus Cl2 goes to form Zn2 plus 2Cl minus. For more complex redox reactions, especially in aqueous solution, additional steps may be needed to help balance oxygen and hydrogen in reactants and products. This is because many species that can be oxidized and reduced, like transition metals, are often bonded to oxygen. For example, MnO4- ions can be reduced to Mn2+ ions. The thing is, it's only the transition metal itself that's getting reduced or oxidized. The oxygen it's bonded to originally isn't. So although the oxygen doesn't actually get oxidized or reduced, we still have to account for it because of the law of conservation of mass. The total number of atoms of each element we start with in a reaction must be the same total number of atoms of each element we end with. So to balance the oxygen atoms out, we can add H2O, because the oxidation number of oxygen in water is -2, the same as it will have been in any of the reactants. We can balance the hydrogen atoms required to produce water molecules by adding H+ ions in acidic conditions or OH- ions in alkaline conditions. For example, as just mentioned, MnO4- can be reduced to Mn2+. Well, to write out the half reaction for this reduction, first of all, we need to track where the electrons are being transferred. So the oxidation number of the Mn in the MnO4- is +7, and the oxidation number of Mn for Mn2+ is +2. To go from +7 to +2, the manganese must gain 5 electrons, so we can add 5e- on the left-hand side. We now, however, need to balance the number of atoms on both sides. Both sides of the equation have 1 Mn, however the left-hand side currently has 4 oxygens. To get 4 oxygens on the right-hand side, we need to add 4 H2O molecules. 4 H2O molecules on the right-hand side require 8 hydrogens, so we'd have to add 8 H+ ions to the left-hand side. This would now give us MnO4- plus 5e- plus 8H+ goes to form Mn2+ plus 4H2O. Notice here that the presence of H+ ions indicates acidic conditions, so to reduce the MnO4- to Mn2+, you'd need to have a solution that contains an acid.